Okay, so now we get to the cross product. The cross product of two vectors is a vector, so it's also called the vector product. And more generally, you can think of it as an outer product or a wedge product, but that's going to be a little bit beyond what we want to do here. So we're just going to call it the cross product. So we have two vectors, u and v, in space, so they have their three components. And now we need to define the cross product, so u cross v, and this will be a vector. So it's going to have the following three components, right? The first component will be u2 times v3 minus u3 times v2. The second component will be u3 times v1 minus u1 times v3. And the third component will be u1 times v2 minus u2 times v1. Phew, right? So this is the definition of the cross product. And if you're wondering how am I going to remember all that, well, remember, you don't have to remember it. You will have a formula sheet, and this will be one of the formulas that will be given to you. As well as the dot product, although that's probably a little easier to remember. Yeah, this one's not easy to remember, and to be fair, I actually don't remember it. I wrote this in such a way up here, right, by doing u on top of v. Here's how I remember it. This involves the determinant. So if you know what a determinant is, and I'm assuming most of you do, the determinant of, well, let's start with just 2 by 2, right? A, B, C, D. So we have a matrix, 2 rows, 3 columns. The determinant is defined as A times D minus B times C. So just multiply the two diagonals and then subtract them in that order. So what happens when you want to take the determinant of, let's say, a 3 by 3 matrix? So instead of using A, B, C, D, E, F, G, all that, I'll do A1, A2, A3, B1, B2, B3 for the second row, and then C1, C2, C3 for the third row. So this is going to be a little more complicated, but hopefully you remember it's just A1 times the determinant B2, B3, C2, C3, minus A2 times the determinant B1, B3, C1, C3, and then plus A3 times the determinant B1, B2, C1, C2. So again, if you remember the adjoint version of the determinant, this is one way to calculate the determinant. There are other ways, of course, using the minor matrices and so forth. But anyways, so this is good to remember, and that's because the cross product can be thought of as a determinant. The first row will just be the unit vectors, I, j, and k. The second row will be the components of u, u1, u2, and u3. And the third row will be the components of v, v1, v2, and v3. So in that sense, a1 is really just the vector I, and then the determinant is, let's see, u2, v3, oh, sorry, I want to write out the determinant, right? So u2, u3, v2, v3, minus the vector j times u1, u3, v1, v3, plus the vector k times u1, u2, v1, v2. So now, when you write out what these determinants are, again, for the 2 by 2 case, it's just this up here. So let's write it out, right? u2, v3 minus u3, v2 times the vector I, and then minus, although I'd like to write it with the plus, so I go the other way, right? I do u3 times v1 first, and then minus u1 times v3. So be careful that this minus sign got absorbed into the subtraction. I switched the order of the subtraction, what it would usually be here, times j. and then plus k times the vector, well, u1 v2 minus u2 v1. And that's the same as the version that I gave up here. Luckily, they all fit on the same screen, so you can compare the two vectors, and they are indeed the same. So this is my little mnemonic device for remembering how to calculate the cross product. Because if you have to look up the formula every time you have to do it, it is going to be kind of a cumbersome way to do that. It really helps to know this. But again, you will have the formula, and maybe when you get enough practice with it, this will become second nature eventually. Right, so quick example, let's just calculate the cross product. Okay, so we have two vectors, u and v, and they have their three components. And I have to emphasize this thing here, right? The vector product, the cross product of these two vectors, right, has to take place in 3 dimensions, has to take place in space. So these are vectors in space. Right. This does not work if you only have vectors in the plane. There is no cross product for vectors in 2 dimensions. There has to be 3 dimensions, otherwise it just doesn't work. Okay, so these are the vectors, and we want to find u cross v, and u cross u and v cross u. So we'll do all 3. So for part A, so this will be part A, part B, and part C. So what's u cross v here? So since I wrote them side by side, that's going to be a little more difficult. I'm going to form the determinant again, because that's the way I like to do it. Okay, so we get a vector with components. Let's see, -2 times -1 is +2, minus 3 times -5 is -15. And then for the second component, we have 3 times 2, which is 6, minus +5. All right, so it's minus -5 times -1, so minus +5. And then for the third component, we have -5 times -5 is 25, minus -4, so +4. So I guess we get the vector 17, 1, 29. So yes, the cross product is not a number, right? It's not a scalar, it is a vector. And that's 29, right? So you can write it this way, or you can write it as 17i plus j plus 29k. Same thing. Okay, so not hard. Again, if you want to just go back and use the original formula here, be my guest. You should get the same answer either way. What about u cross u? So as a determinant, we have I, j, and k. And then we have the components of u. And the components of u again, right? We're taking the cross product of u with itself. And again, for those of you in linear algebra know that when you have 2 rows identical like this, the determinant is automatically 0. But if you don't know that, let's write it out, right? So this is going to be -2 times 3 is -6, minus -6. And then we get -15 plus 15. And we get positive 10 minus 10. So 10 minus 10. So, yep, the first component is 0, the second component is 0, the third component is 0. This is just the 0 vector. Right? So, if that looks like a coincidence, it's not. If you take the cross product of any vector times itself, you always get the 0 vector. All right, last example, part C, we want v cross u. Oops, cross u. In other words, sorry, it should be a u. All we're going to do is interchange the second and third row. So the second row will now be 2, -5, -1, And the third row will be -5, -2, and 3. And you do the same thing, right? We get -15 minus 2. We get 5 minus 6. And then we get -4 minus 25. So now we get -17, -1, -29. So that should look familiar, right? If you look at part A, all the components were positive. In part C, we got the same numbers, but they're all negative. In other words, this is really just the opposite of U cross V. So whenever you take the cross product in the opposite order, it turns out you don't get the same thing. The cross product is not commutative. It's anti-commutative. You get the same vector, but it points in the opposite direction. Okay, so that's going to be our first property. So now we have, again, a theorem with all the properties. Okay, so we have three vectors, u, v, and w. These are vectors in space, and these will not work if they're vectors in the plane. C is a real number, right, or a scalar. Okay, so the first part is what I just mentioned, that if you take the cross product of u and v, and you take the cross product of v and u, you do not get the same thing. You get the opposite. Okay, so, right, not like the dot product where you get the same thing when you change the order. When you change the order in the cross product, you get the opposite vector. Okay, second property just says that the cross product distributes over sum. So if I take u cross, let's say v plus w, I can just as well take u cross v and then add to that u cross w. So in fact, this does work the same way as the dot products, but the difference here being that these are vectors. So you're adding two vectors, not two numbers now. Okay. The third property is, again, very similar to what we did for the dot product. If we have C times the cross product u times v, or sorry, u cross v. Yeah, don't say u times v, right? It's u cross v. It's a cross product, right? There is no general way to multiply a vector u times a vector v. It turns out you can, but it's not a vector, right? More generally, this is something called a tensor, and we're not going to get into that, right? You have to do something called the tensor product. Okay, so we're not multiplying vectors. We're taking the cross product of two vectors, which is one way to multiply them, I guess, right? So you can guess that if I just take C times U first and then take the cross product with V, I get the same thing. Or if I take U cross C times V, I get the same thing. So that's no different than the dot product. The fourth property is if I take the vector U cross the zero vector, well, you get the zero vector. After all, if one of the rows of the determinant is all zeros, then you just get 0, 0, 0. Right. And of course, if you take 0 cross u, sorry, not dot u, 0 cross u, you also get 0. So remember, in number 1, you get the opposite, but if you take the opposite of the 0 vector, you just get the 0 vector. So this is one situation where the two vectors do commute if one of the vectors is 0. Okay, and then the fifth property, there's another way to get the 0 vector. If you just take a vector cross itself, you still get the 0 vector, right? Even if u is not 0. Okay, so we saw that up here, that u cross u is the 0 vector, right? And then there's a sixth property, which I guess we'll mention now. If I take the vector u, and I take the dot product with v cross w. Should be v cross w. Okay, so I have a vector u and a vector v cross w, and then I take the dot product, right, which gives me a number, a scalar. It turns out that you can get the same number if I take u cross v first and then take the dot product with w. Right. In other words, if you switch the dot and the cross, amazingly, right, you get the same thing. You get the same number. Okay. Yeah, now we need parentheses here. The one thing you have to be careful of is if you try to switch the parentheses. If you do u dot v cross w. Right, so think about this for a second here. This makes no sense. Right? This just doesn't make any sense. This is not a vector, it's not a number. Right? If you take u dot v, you get a number. Let's call that number c. So how can I take a number cross a vector? Right? When we defined the cross product of two vectors, they both had to be vectors. Taking the cross product of a number and a vector is nonsense, right? It's meaningless. There is no such thing. So don't do that. Don't make that mistake, right? So here we really do need the parentheses. We have to do the cross product first to get a vector, and then a vector dot a vector makes sense. Right. And by the way, we didn't mention this, but it's the same thing. You can't take a number dot product with a vector. That also makes no sense as well. You can take the dot product of two vectors, but not the dot product with a number and a vector. Right. So that also makes no sense. Okay, so those are just some properties. And again, I didn't prove any of them, but some of them made sense in light of what we did up here. And then the others will make more sense as we talk about the geometric properties. So let's do that now. Okay, so next set of properties, this is Theorem 11.8. U and V are vectors in space, and theta is the angle between them. So we have the same picture here. U and V are these vectors, and theta is just this angle between the two vectors, right? Okay, so the first property tells us the direction that u cross v points in. Okay, so u cross v as a vector is going to be orthogonal to both u and v. So what that means is the vector u cross v will be perpendicular to u and perpendicular to v. So, and maybe I just didn't quite draw the right picture here, but let's try it again. So here's the vector v, and here's the vector u, and let's suppose these two vectors sit in a plane. Let me try to draw that plane here. Is that good enough? Right, so these vectors, right, span this plane. The vector u cross v then will be perpendicular to that plane, or normal to the plane. In other words, it's got to point directly out of the plane here. So that's the direction of u cross v. It's going to be perpendicular to u, and it's going to be perpendicular to v. Right? So, yep, if this plane, if you look at it from the side, right, u and v point this way, then u cross v has to be perpendicular to that, right? Although it could point downward as well. That's also perpendicular. But it turns out not to in this case. So how do you know which direction, up or down, it points in? That's determined by the right-hand rule. And this is where in class I would show you my right hand and show you the direction here. If you point your fingers in the direction of u first, right, because u is the first vector, and then curl them in the direction of v, so curl your fingers in the direction of v, your thumb will point upward, right? It points in the direction of u cross v. Okay, so, right. So the direction of u cross v follows from the right-hand rule. Because if you use your left hand, you get the wrong answer. You would get that u cross v points downward, but in this setup it doesn't, right? So this is the right-hand rule that picks out the direction of u cross v. Okay, so that's the direction. What about the magnitude of u cross v? Oh, sorry, I'm going to use the same color blue here. So if we only want the magnitude, after all, the direction is given by the right-hand rule, and it's perpendicular to both u and v, or orthogonal to u and v. You can get the magnitude by taking the magnitude of u, right, times the magnitude of v. Look familiar? Right. So I can't say cosine anymore because that would be the dot product. So for the cross product, it's the sine of the angle between the two vectors. Okay, so that gives you the magnitude of the cross product. Now be careful, right? You cannot use this to just find the cross product, because this will not give you the direction, right? This is a number, a scalar. So this is only the magnitude or the norm of the vector. We talked about magnitude or norm of the cross product. It will not tell you the direction. For that, you have to go back to part 1, right? Or you can just calculate the three components. Did we do that? Yeah, like up here, calculate the 3 components, and that will also tell you the direction. Right? Okay, so third property, if u and v are parallel, if they are parallel vectors, and we talked about that in, I think, the last video, or sorry, 2 videos ago, two sections ago. It was in 11.2. 2 vectors are parallel, then their cross product is 0. Okay. So essentially, if I'm running out of space, but if 2 vectors point in the same direction, right? If this is u and this is v, their cross product is 0. Well, one way to see that is, what's the angle between the 2 vectors? The angle is 0, right? 0 degrees, 0 radians. What's the sine of 0? 0, right? So it doesn't matter what their magnitudes are. You just multiply the product times 0 and you get 0. So that tells you that the magnitude has to be 0. But, right, if the magnitude of a vector is 0, then there's no choice. That vector u has to be the 0 vector. Right? The only vector with 0 magnitude is the 0 vector. Okay, so that tells you that u cross v has to be 0. And I think I can squeeze in one more here, although this is also going to be a geometric formula here. So if you look at the vectors u and v here, and I just kind of put them in the plane, you can form this parallelogram. And I know it almost looks like, well, it sort of looks like a rectangle if you're assuming that the angle between u and v is 90 degrees, but let's just say it's not here, right? So let's say that this is a parallelogram, right, formed by the vectors u and v. So we already talked about how to get u plus v. That's just going to be this vector here, right, the diagonal. And then u minus v will be this vector here, the other diagonal. But here we just want to find the area of that parallelogram. And to get that, well, so the area of the parallelogram, G, right, with adjacent sides u and v. So the 2 adjacent sides are the vectors u and v. Okay, again, that's this picture up here, or if you prefer, this one up here. So same thing, I just moved it up. So that area is given by the magnitude of the cross product, right? Remember, area is just a number, so if you take the cross product, make sure you remember to take the magnitude of that vector to get the area. Right? So yeah, in fact, if you know the two sides, and another way to get the area of a parallelogram, I'm going to draw a little parallelogram here. Right? So let's say this is side A, side B, and then this is angle theta. The area is just A times B times the sine of theta. So in this case, it's the magnitude of u times the magnitude of v times the sine of theta, which is the same formula that we got in part 2 up here. So number 4 just tells you that that number also represents the area of the parallelogram. Okay, so not hard to calculate. Oh, and if you want the area of, let's say, the triangle here, say just this area, well, really that's just half the parallelogram. So then take this area here and just cut it in half, or divide by 2. So that'll be the area of the triangle. Okay, so I think that's it for the properties. Okay, so we can go on to this example here. We want to find the moment of the force F given by these components, -4, -3, applied to a point Q with coordinates 5, -2, about the point P, which is the origin, right? So point P up here, this point P is just 0, 0, right? And point Q has coordinates 5, -2. And then the vector F, right, so that's the force applied, has components, -4, -3. Right. Sorry, components. Yeah, not parentheses. There we go. Okay, so that's the situation, right? So how do we find the moment? Well, what do we mean by moment? Again, for those of you who have not taken physics or engineering, probably don't know what that is. So let's define, right, it's the moment of a force so force F as a vector, right, applied to a point Q, about point P is given by the following, right? It's going to be the magnitude of the vector from P to Q cross the vector F. Okay, so this is what we call the moment. I guess I'll use, well, I hate to use M because we use M for a lot of other things, but M for moment is fine here. Right, so it's a number, right? It's not a vector because it's the magnitude of the cross product. The cross product itself might be, you know, a vector, but then the magnitude will be a scalar, right? So that's what we're gonna use here. So, right. So this was a little deceptive when we described the force F with these two components, right? Because this is taking place in the xy plane. Unfortunately, when we talk about the cross products, remember they can't be vectors in the plane. They have to be in space. There has to be a z component here. So what we're going to do is kind of cheat a little bit. We're going to say that the vector force F has 3 components, right? It has a component -4 in the x direction, -3 in the y direction, and then 0 in the z direction. Okay, so this is now a vector in space. Okay, and likewise, if we find the the vector from P to Q, right, it's just the vector 5, negative 2. But that's a vector in the plane. We need a vector in space, so we're going to do the same thing. We're going to say that the x component is 5, the y component is negative 2, and then the z component will just be 0 again. Okay. So the problem is that these two vectors live in two different two different environments, I should say, right? The vectors up here are in 2 dimensions. The vectors here are in 3 dimensions. But in order to take the cross product, it really helps to write them this way so that we can use the definition of the cross product, right? So yeah, now there's no issue. We can take PQ cross F and find that vector, right? So using the usual determinants again, although you don't have to, but that's the way I like to do it. Zero. So, yep, so for the I vector, you get negative 2 times 0 plus minus 0 times negative 3, so minus 0. And then for the j component, we get, well, 0 minus 0. And then for the k component, we get negative 15 minus 8. So that's just going to be 0i plus 0j minus 23k, which you don't need the zeros here. This is just the vector negative 23 times k. Okay. Or if you do write it with components like this, then you have to write the zeros, of course. But when you write it as a linear combination of I, j, and k, you don't need the zeros then. All right, so that's not the moment, that's the vector. Now to change that to a scalar, we just take the magnitude of that vector, which I hope you can do pretty easily. It's just 23. I mean, officially, it's the square root of 0 squared plus 0 squared plus negative 23 squared, right? And you can work that out. I don't know what 23 squared is. Okay, it's 529. So you get the square root of 529, which is, of course, 23. So that's the moment, 23. So units, what are the units? Well, we didn't give you units here, but if force is in newtons and distance is in meters, it can be 23 Newton meters. If force is in pounds and distance is in feet, this would be foot pounds. But again, let's worry about that in your physics classes or engineering classes. So I'm not quite that concerned about units here because I didn't give you units in this problem. So in this case, the moment is just a pure number. But typically, these are the units of units. It's a force times a distance, so Newton times meter, or foot times pound, or foot pounds, yes. Or ergs, I guess, but let's not get into that. So this also has units of energy as well, but that's a completely separate issue. Okay, so that's really all I wanted to do. Maybe we should mention one more property, or one more quantity, and that's the triple scalar product. So again, here we have 3 vectors, u, v, and w, all with the usual components. I'm not going to write them out again. And we can form the following product. We can take the vector u dot v cross w. And in fact, we did mention this once. We mentioned it when there was this property that we can also do u cross v first, and then dot w. So it's the same thing, but let's focus on this quantity here. Right. We can calculate this quantity by just taking the following determinant. Right? Remember, it's a number, so it'll be the determinant whose rows are the components of the three vectors in this order, u, v, and w. So you take that determinant and you get the answer, right? And you can show that just by taking the components of these vectors. But this gives you a very easy way to calculate the triple scalar product. Remember, it's a scalar, right? It's a dot product, so it's a number. The significance of this number. So geometrically, if you form three vectors, let's say this is the vector u, let's say this is the vector v, and these are all in space, and let's form this vector w up here. So we know that v cross u, or u cross v, the magnitude of that will be the area of this parallelogram. So the triple scalar product will be the volume of this object here. So it's certainly not a cube because the sides are, well, tilted here. Very hard to draw straight lines here, but let's try that one more time. Okay, so think of a cube that you kind of apply like a shear force to, like you're almost twisting the cube, right? So this is called a parallelepiped. Right. So this is just the volume of that object, of that parallelepiped. Okay. Yeah, and you can compute it two different ways, right? You can compute it this way or this way. It gives you the same answer. Again, geometrically, that might be kind of hard to do. Right. Oh, actually, we have to be careful here. This dot product might be negative, in which case it's not the volume. So, okay. So the volume, right, is the absolute value of this triple scalar product. Okay, so don't forget to take the absolute value, right? The volume can't be negative, right? This dot product here could be positive or negative. So the triple scalar product could be any number, positive, negative, or even zero. Well, then that would give you zero volume, right? So when would that happen? Precisely when any of these vectors are parallel, I think. If u and v are parallel, or w and v are parallel, or u and w are parallel, then that gives you a zero dot product. I think that's it. Yeah, I mean, I guess I could look for one more example, one more quick one. Okay, so here's a good one. Find a unit vector orthogonal to both u, which is 4i minus 2k, and v, which is I minus 3j plus k. Okay. So, yeah, if it helps, you might want to write them this way, right? So this vector u has components 4, 0, negative 2, right, because it's 0j. And then the vector v has components 1, negative 3, 1. Okay, so we need a vector that's perpendicular to both of them, right? So if this is the vector u and this is the vector v, we need a vector perpendicular to both v and u. Well, easiest way to do this is just take the cross product. If you take the cross product of two vectors, by definition, it has to be orthogonal to both of those vectors. So, yep, easiest way to do this is to take your cross product. So we get 0 minus 6. And then the second component will be negative 2 minus 4. That's also negative 6. And then the third component will be 4 times negative 3 minus 0, so negative 12. So -6, -6, -12, or if you prefer, -6i minus 6j minus 12k. Okay, so that vector will be orthogonal to u and orthogonal to v. Yeah, but we're not done, right? They want a unit vector. So does this vector have magnitude 1? Not likely, right? So how do we find a unit vector? Well, I'm trying to come up with a name for this. Oh, how about just W? Right, let's just call this W. So you know how to find a unit vector in the same direction. We talked about that in the previous video. That's just taking the vector and divide by its magnitude, right? Or to spell it out, it's just u cross v divided by the magnitude of u cross v. Right? So what's the magnitude of this vector? Well, square root of -6 squared, right, plus -6 squared plus 12 squared. So I get 216, or rather the square root of 216. And that's going to be, well, it's 6 squared of 6, or approximately 14.7. Right. But we'll leave it as 6 squared of 6, because I think you know where this is going. You just divide each component by that number. So you get a vector with components -1 over the square root of 6, -1 over the square root of 6, and then -2 over the square root of 6. And that's good enough. Remember, you do not have to rationalize the denominator. No longer is that required. You know, if you did, well, you would get the following vector: -square root of 6 over 6, -square root of 6 over 6, and then -2 square root of 6 over 6. Oh, which is -square root of 6 over 3. Right. So either way, and you can write them with ij's and k's as well if you like. So that's it, right? So to find a unit vector orthogonal to two vectors, take the cross product of those two vectors and then normalize it, right? Normalize it means change it to a unit vector, and you can check that this is a unit vector now. And that's it. So rather than do another computation like this, which I think most of you probably should be able to do, this is one of the later ones, and it might be for homework, but that's okay. So the question is this: if u is not the zero vector and u cross v is equal to u cross w, can we say that v and w have to be equal? Is that true? So it's basically just a true or false question, right? So the idea is this, right? U cross v equals u cross w. Can we cancel the u's, right? As long as u is not 0, obviously if u is 0, then these are both equal to 0. So clearly v and w would not have to be equal if that's the case. But if u is not the 0 vector, can we just cancel the u's like that? I mean, that's the question, right? Does this imply that v is equal to w? So not an easy question, right? Not one that's, well, it's not one that's easy to just think about in the abstract like this, right? I mean, it seems reasonable that it should be. But the question is, can we find an example where this might not be true? So if you think it is true, right, let's start playing with numbers here, right? Let's I don't want to use green here. Let's use yellow again. Let's just keep it pretty simple here. Suppose u is the vector 1, 0, 0, right, which is I. Suppose v is the vector 0, 2, 0. Well, let's not even do 2. How about just 0, 1, 1? And let's suppose w is the vector 1, 1, 1. Okay. So let's see if this works, right? If it doesn't work, then it's not going to work in all cases, right? If it does work, well, that doesn't mean it's true. It just means that it happens to be true for these vectors here, right? So if it does work, this is still in question, right? All right, so let's just take u cross v very quickly here. It's going to be, let's see, 0, and then negative 1, 1. So, wait, u cross v, yeah, that's right, u cross v, and now u cross w. That's going to be a little trickier because this is u and w here, so that's the determinant we want. We're going to get 0 minus 0, so 0. And then we get 0 minus 1, so that's still negative 1. And then we get 1 minus 0, which is 1. Right. So these are certainly equal. U cross v is equal to u cross w. Right? It's the same vector. Unless I made a mistake, maybe I should double check here. Let's see, 1, 0, 0, so I, j, and k, and then w is 1, 1, 1. So the first component is 0, the second component is negative 1, and the third component is definitely 1 minus 0. Yep. Did I do the first one right? 0, 1, yeah, negative 1, and then 1. Yeah, I think that's it. So can we say that v is equal to w? Well, no, not in this case, right? This is the vector 0, 1, 1. That's not the same as the vector 1, 1, 1. So v is not equal to w. So clearly, the answer is no. This is false. This is false, right? And again, maybe I got lucky because in other cases, if you just make up 3 random vectors, it's possible that this will be true, but not in this case, right? So as it turns out, yeah, you have to be careful when talking about the cross product. You cannot just cancel the u's here. That's not necessarily going to work. And it didn't work in this case. It did not work in this case. And it doesn't work in general. Right? You can maybe come up with an example where this is true. Right? You can find 3 vectors where this does work, but it's not guaranteed to work. So in general, it's false. Right? What would have to be the true here for this to work is actually the next example. So if u is not the 0 vector, right, and if you take u cross v and that equals u cross w, and if the same thing is true for the dot product, in other words, if I take u dot w, if that's u dot v first, if that's equal to u dot w, right, if both of these are true, then we can say for sure that v is equal to w. Right, so that turns out to be true, although that's kind of hard to show. But yeah, so what's going to happen here is if you take u dot v, in this example up here, you do not get u dot w. Right. U dot v is 0. U dot w is 1. So that's not true here, even though this is true. So that's why, right, that's why we can't cancel the things here, right? So again, that's just kind of a little bit more of a conceptual question, but you know, they're ones that you want to think about a little bit. Or, if it's hard to think about, then just plug in some numbers and see if it works. Okay, so that's the cross product.